Hey, so a couple weeks ago on the forum, a sort of a repeat of a previous question came up, and it was about training a Stardist 3D model um, using like 2D, starting with like a 2D model. And you can find this question if you go to forum.image.sc, search Stardist Connect 3D, and so the new question is this one here, training Stardist 3D model, and the sort of a repeat of a question that came up in January. So looking for more information on this video, check out these two questions. I'll post links to the notebooks on there. And in case you're looking for the notebook that goes with this question, you can find it on my, I have sort of a GitHub repository called True North Intelligent Algorithms, TNI a Python, which is basically where I put utilities and experiments and stuff. Some of it's not that polished, just to warn you, but I have sort of a notebook folders, and some of the questions that I've helped with on ImageSC are sort of organized by date. And this one I think was from January 30th. So you could find it, yeah, here, 2024-01-30, connect 2D and 3D. And it first came up a few months ago, and then it came up again just recently. So I was really glad it came up again because there's some imperfections in my first run through this, and I wanted to address them and just revisit the problem a bit. So what are we doing here? So the end goal is to come up with a 3D Stardist model. And we could maybe manually generate a bunch of 3D labels, but that could be a lot of work. You know, like if you have an image with 100 slices, you know, sometimes in 2D, labeling an entire slice is not so bad, but if the problem size is multiplied by 100 in 3D, labeling 100 3D slices is a lot of work. So there's some strategies, you know, that can really help with that. And one of them is using Stardist 2D, predicting 2D labels, and then like connecting them in 3D. So this notebook goes over how to do that. And like I said, you can find it on GitHub. First part of the notebook just goes over some of the dependencies that you need. If you have any trouble installing any of these, or I messed up the instructions, yeah, just post on the forum. So then I, you know, do some imports and then set up paths for my project. Then I create a 3D point spread function. So the reason for that is that I'm going to be doing a simulation here. So I want to start with by like creating fake objects, but then add blur and noise to try to sort of simulate real microscopy images. Import Stardist, and then in this little loop here, I generate image and ground truth pairs. So that's done with a few steps. Create a phantom that's going to contain random spheres. Apply blur and noise in 3D. Then apply like a random shift to each slice just to make them a little bit more imperfect. Because one of the goals of this exercise is to see how robust Stardist is to like imperfect input labels. Then we normalize the image, and then apply 2D Stardist slice-wise to a 3D image. And I do that part, when I do that part, I use a little helper utility that I've written. So a lot of my examples rely heavily on like little utility libraries I've written and little helpers. And that's one of the reasons I can do them fairly concise, like do a lot of stuff in one notebook. There's often a lot of code behind it in these utility libraries. So if you're really getting into Python and deep learning, I totally recommend you start doing like your own utility libraries and everything. Because like half the battle with all this stuff is just developing like a bunch of helpers so you can organize data the way you want. You could do like a lot of the busy work sort of behind the scenes a bit. But anyway, I got a couple of utilities to do to apply Stardist 2D slice-wise. And again, if you go to my TNIA Python repository, you can track these down and see how they work. And if they're useful to you, of course, you're welcome to reuse them. So I have the Stardist, apply 2D slice-wise, and connect 2D and 3D. Okay, so this little loop basically creates a bunch of simulated images. And I do a little, for due diligence, I take a look at them. So you can see these are 3D images with noise and blur added, and then we generate labels with the Stardist 2D and connect them in 3D. So they're a little bit imperfect. Okay, important question. Wait a minute, this is a simulation, right? So don't we already have like the absolute ground truth, like where we started from in the simulation? Right, of course. And when I do these simulations, that's like a point that's a little bit confusing, because I have like the total ground truth and then like a ground truth I make after that. Because a lot of times what I'm trying to see is not how well the network will train if I give it the absolute perfection, but I want to like also simulate like the process I have to go through to generate labels. It's a bit confusing in some ways, but what we're trying to see is like, even if my labels aren't perfect, if I go through this, like will Stardist still learn okay? And then you could then depending on what we find out, we could maybe go on to real images after that. So yeah, in other contexts, you could do a simulation and then use like the starting point ground truth or whatever you want to call it. But anyway, okay, so did I confuse you? Maybe, but let's use Napari to try to unconfuse you. I'm going to pop up Napari. And just wait a second here. Okay, there it is. So we got Napari here. And so we have three things. We have image, ground truth, and 2D connect in 3D labels. So let's start with image. There we go. We got this image. It's got these spheres in it. Ground truth. This is like what the first thing I generated. I generated this ground truth, and the image was created by blurring and adding a little bit of noise to the ground truth. Then what I did was I used Stardist 2D and the connect in 3D strategy to, basically test the process I'd use in real life. Because in real life, like this, in real images, this perfect thing here isn't available, right? All you have is the blurry, noisy image, and you have to like either hand label it or come up with some other strategy to make labels. So that's what we got here. These imperfect labels that we generated with Stardist 2D, and what we want to see is, so if we use Stardist 3D, this is a training set for Stardist 3D. Will it actually do better than the training data? Okay, why would it do better than the training data? Well, because of the model is basically constrained to be star convex. So it may not overfit these imperfections, these sort of random imperfections. So we might get much nicer objects. We might actually get much more spherical objects out of the model, but we'll train it and we'll find out. Okay, so we generated a training set, and now we're going to train in 3D. So this is cool. Like, I think a lot of the examples I've been doing, the bees and everything, are 2D, but 3D examples are really fun. So first we just do our imports. Then it's always a good idea to check, just make sure the GPU is available, because you can mess up a lot of ways. Sometimes when you install Stardist or the GPU drivers, you mess up and it only sees the CPU, and oftentimes then it's just really slow, and you don't know why. And in 3D with big images, the problem becomes sort of even worse. So good idea to just confirm GPU is there and everything's connected right. Um, then we define our model path and load our corrupted images and our ground truth images. And again, I have some utilities that I've made to do this kind of thing. Again, you can, if you get this code, you can inspect my utilities. I recommend if you really get into Python deep learning, you start writing your own like utility libraries. It's really helpful. But yeah, but I load this training set, and then I always take a look at the sets of like inputs and ground truths just to make sure like I didn't mess up anything. Shuffle the data sets, not really needed. I mean, I only have 5 in this case. It's a small simulation, but sometimes when you have a lot of data, you want to shuffle it. So you add a little bit of, you're not always training in the same order. Okay, so then we grab Stardist and okay, and actually before I go on to the training step, just another quick thing. So you hear on forum questions, you hear people, it's not working, something's going wrong, it's only giving me like 2 dimensions when I try to calculate the anisotropy. Maybe something went wrong when you're like loading the data or with the file reader, who knows? So it's always a good idea, like pretty simple, just output when you load this training data. I mean, I'm visualizing it, so I know it's 3D, but it's also a good idea to output the actual dimensions, just so you confirm it's actually for Stardist. You need to confirm it's 4D. So there's also this subtle point where you have to add, like if you have like one channel data in Stardist, you have to add like a trivial channel, so you get you actually get 4D data here. So you just check like your input shape and your ground truth shape is what you expect. And if you have any, if you have some Stardist problem or some other deep learning problem and you think you might be having some dimension mix up or something weird, just again output this kind of stuff and post what you get on the forum, and maybe somebody could help you. So anyway, okay, yeah. So then we with Stardist 3D, we often do this thing where we compute the extents and the anisotropy, and it's just like, especially with microscopy, our objects are like asymmetrical in the 3rd dimension. So we calculate that and we end up feeding that back into the model. Then we create a model here, and my hope is, so this whole purpose of all this is like, I want to train on this sort of irregular data, but get more spherical like outputs. And a couple of parameters you can play with if you're doing this just to yourself. So notice here I've set the number of rays to 96. However, if you know that your objects are like fairly symmetric and spherical, you might be able to lower this and you can get a smaller and faster network. And you also it may be more robust to like noisy data. But anyway, this is the code that sets up the model. Any questions about this, again, you can post on the forum. So then we train it. And I did the training beforehand, just again. You don't want to spend 40 minutes in a video training. And yeah, let me go back for a second. So yeah, this is probably not the most polished video ever, but that's not the point. Like the point is just to try to convey maybe some information that could be useful to somebody. So like I just mentioned, I pre-trained this model, but one thing when I go back to it, so there I have this little new model flag. So if I want to go back and like run a test on the model that I pre-trained, I just set this flag to false and I have a little if statement. And in Stardist, you can, if you want a new model, you feed it a config file. If you want to just grab an old model, just don't give it a config file. And if the old model exists, it'll like reload it. So in this case, there's all this training. Yeah, so I did a bunch of training and that was done beforehand. What I want to do is just load the model back and take a look at it. So I loaded the model back and then you could just like apply it. So Another problem with this little experiment I did is really low sample size. I've only used 5 images, so who knows? I might be overfitting a little here. Um, but again, the real purpose of all this is just because I wanted to test whether Stardist models, if you feed it really noisy, um, uneven, like 3D labels generated by this 2D connecting 3D strategy, will the actual 3D model be like smoother and more symmetric? And the outcome of this is, yeah, I think it is. Like so what you're looking at here, finally I applied the model that I trained, and here's my 3D image, my labels that I generated with the 2D connecting 3D strategy, uneven, imperfect, and the trained model is a little better. Let's look at it in Napari. Okay, so go to the 3D view. Here is, okay, yeah, and I gave these bad names because I labels and labels. We don't know which is which, but that's another thing I'll have to fix. But I'm not going to redo the entire video just for that. Anyway, like I said, an imperfect video and imperfect labels too. But these were the imperfect labels that we trained Stardist on, and the trained model is actually, better. And this is not surprising, again, because it's star convex model, and it's not, if it's not overtrained, it's not going to learn. It can't learn like all these random imperfections. Yeah, so I think that's it for this video. Hopefully somebody finds this useful. That's it for this one.